Hi, and welcome back to my SAT and AP Physics 1 subject video test. What I want to do in this video is gain a better understanding of latent heat transformation and how heat is transferred between two bodies. To redefine latent heat transformation, latent heat of transformation, latent heat is the amount of energy released or absorbed by a body during a transition between states of matter. So it is the energy gained or released by a body or system during a change in a state of matter. At least that's how I defined it in the last video. But what I want to do in this video is give you a better understanding of latent heat and also a formula that we can use to find the exact amount of heat needed to change a liquid from a solid into a liquid into a gas, and a gas back into a liquid. And using this new definition, I'm going to cross that out and do this in new color. And this new definition I'm going to say is that latent heat is the heat required, so the heat required to change a mass of a substance, a mass of any substance, from one state of matter into another. So from a solid to a liquid and vice versa. And a liquid to a gas. And vice versa. It is also possible to have latent heat of transformation between gases and solids. If you remember in the past video, we talked about sublimation and deposition. Sublimation is this process right here, when we take a solid and we go into a gas. And deposition, otherwise known as desublimation, is the vice versa. We take a gas and it immediately transforms into a solid. Okay. From this definition, we can see that latent heat of transformation depends on two things. The heat inputted into an object. So, heat inputted and and the mass of the substance. So it's the mass of said substance. Mass of substance. And from various experiments, we've actually shown that the latent specific heat, L, is directly proportional to the amount of heat added divided by the mass of the substance. So using this formula right here, we can find exactly how much heat is needed to transform a solid into a liquid into a solid, a liquid into a gas, and gas back into a liquid. Let's take a look at an example. If we had pitcher of water. So here's our bucket or pitcher, whatever we want to call it, cup. And we want to fill it up with some water. And let's say it has a mass of 10 kilograms. And we input 30 joules. If you plug it into this equation, if we plug this back into our equation, we're gonna put the mass on the bottom, so we're gonna have 10 kg, and we're gonna have 30 joules up at the top. And from this, we can see our latent heat. We can see that our latent specific heat is 3 joules per kilogram. And what this means is that we require 3 joules per kilogram to convert 1 kilogram of this water into either a solid or into a liquid. So that's what we're going to cover about latent heat of transformation. And now let's talk about the different ways heat can be transferred from one object to another. The one that we're most common or most familiar with is conduction. Conduction is a transfer of heat via direct molecular collision. So transfer of heat via direct molecular collision and what happens between these molecular collisions? Well, what's actually happening is that we have a transfer of kinetic energy. And remember from the past video, a high kinetic energy, so a high kinetic energy is a hot substance, so it's high in temperature, but a low kinetic energy is a cold substance. So we have a cold substance. And how does this exactly work? If we have a liquid, let's do this let's say that we have water. Water's our liquid again. Boring, yeah. So we have this puddle of water. It looks like that. And we have molecules in here. There's a lot more than what I'm showing, obviously. But we have molecules that are moving in their own separate directions. And they're going the way that they want to go. They're colliding, they're bumping into each other, and they're interacting with one another, but on a scale so that it doesn't necessarily matter. If we put this piece of water in contact with a block of ice, well, we intuitively know two things are going to happen. Either that this ice, or this puddle of water is going to transform into ice, or that this block of ice is going to transform into a puddle of water. Either way, the same thing is going to happen on a molecular level. And inside of this ice cube right here, we have molecules that are set up in a lattice. In a grid-like structure, they're compact, and they're not moving at all, more like vibrating in place. Again, there's a lot more molecules than what I'm showing here. And so if we put this block of ice on top of our puddle of water, here's our puddle of water, and here's our block of ice on top of it. And let's zoom in on this face right here. So we're going to zoom in on this right here. Let's make this screen a little brighter. If we take a look at a 2D, we can see that our puddle of water, if that's our barrier, our puddle of water, our molecules are fast moving. They're like this. They're going to go in here. And then our block of water is rigid, or sorry, our ice is rigid, and it looks like this. So what's going to happen is that these molecules are going to eventually bump. This is going to bump into one of these molecules over here, and they're going to transfer kinetic energy. And we take a look at this. A transfer of kinetic energy directly correlates to a transfer of temperature. If we have more kinetic energy, we get hot. So, when this molecule bumps into an ice molecule, energy from this is transferred into here, and this guy is going to break free. He's now free, and now he's moving around. He's going to hit other molecules, and now his kinetic energy increases. So that's conduction. So that's a heat transfer by conduction. It is a direct molecular collision. To once again refine this, conduction is a transfer of kinetic energy through molecular collision. So a transfer of kinetic energy through direct molecular collision. All right. Now let's take a look at our second example. Let's pull out this orangish color right here. Our second example that we're going to talk about is convection. So heat transformation via convection. An easy way to think about heat transformation by convection is heat transformation through a medium. To define this specifically, the heat, so the energy or heat generated by a source, heat or energy generated by a source that's generally mobile, generated by a source migrates away from the source through a separate medium. And this medium are generally gases or liquids. So there can either be a gas, such as air, or it can be a liquid, such as water, again, or really any moving source that's either a gas or a liquid. Alright, if we take a look at an example, let's say that we have this blackish candle right here. I'm going to color in really quickly. It's kind of bad. And we have a wick right here, and we're going to have fire coming out of it. This is lit, and we have a fire coming out. Well, the air particles around it that I'm going to depict in this light bluish color, the molecules around it, they're going to heat up. So we have air molecules all around it. And the molecules over here, they're going to heat up. And I'm going to show this by showing red. And from other science classes, we know that hotter air is less dense than cold air. So what's going to happen, let's just zoom in on the air molecules. So what's going to happen is that at the top, we're going to have hot air. Hot air like that. And then, once again, around the flame, we're going to have cold air. So the hot air is going to rise around. It's going to rise around and above the cold air. And so we can draw our flame in again, but that doesn't make a huge difference. So the wick's down here. We have the flame that's going to come out like that. It's a different shape now. That doesn't really matter. But over time, once again, this cold air is going to heat up. It's going to heat up. And it's going to get to the point where it's hotter than this original set of hot air. And they're going to move up and around this. So that's heat by convection. Heat by convection is heat or generated by a source. And that heat / energy migrates away through a separate medium, either through a gas or a liquid. A liquid example could involve a hydroelectric dam and water. The water flows through, creates energy, and then the energy doesn't really flow away, but the water is now at a different temperature, and it's also at different acidity or bases or alkaline levels, but that's neither here or there. The temperature that it gains by going through the dam generally increases, and it's hotter on the other side, and it's going to carry that hot heat to the other side and far beyond. And we're going to take a look at our last type of heat transformation, which is special for two reasons, which we will go over in green. That's sort of green. All right, let's see here. Our last heat transformation is through radiation. Radiation is unique since it's a transfer of heat through electromagnetic waves. More specifically, it's a transfer of heat through electron orbital paths. So it is a transfer of energy through electromagnetic waves. Like I said earlier, the first reason why this is important, because energy is actually transferred by the electrons of the electromagnetic waves, so EM waves, and another object. Generally, these EM waves look something like that. Not really. But anyways, they have electrons. If we can assume that this is that this is the core of an atom, and we have electrons that are flowing around it, when an EM wave hits one of these electrons are now going to move to a higher valence. And at this higher valence, they have more energy. And because they have more energy, they're moving around more rapidly. And if these are moving around more rapidly, then the entire molecule is moving around more rapidly. And if the entire molecule or atom is moving around more rapidly, then we have a higher kinetic energy. And in turn, which increases our heat. So the electrons are excited. So electrons excited, which increases the kinetic energy of the electron, and in turn, the kinetic energy of the atom, which in turn increases the kinetic, and an increase in kinetic energy increases temperature. And the second reason why radiation is really cool and really important is because it does not require a medium to travel. Because electromagnetic waves are unique since they're not really a transfer of energy along any specific medium, but rather photons and electrons that are compacted with one another that hit other molecules and therefore excite those other molecules and electrons. So to summarize, our three types of heat is conduction, convection, and last, but certainly not least, radiation. Conduction, let's use some more readable color actually. Conduction is a transfer of heat through direct molecular collision Convection is a transfer of heat through the movement of a medium that's either a gas or a liquid, and heat transformation by radiation is the transfer of heat through electrons. or better put, electromagnetic waves. So these are three types of ways which heat can be transferred. And to quickly summarize, latent heat of transformation. Latent heat is the heat / energy required to change a substance from or between states of matter. It is given through the equation: the latent specific heat is equal to Q divided by the mass. It is directly proportional to the amount of heat added to the amount of mass. So if the amount of mass decreases, latent specific heat increases. If the mass increases, the latent heat decreases. So what that means is that with the decreasing mass, we're going to require more. We're gonna have a higher specific latent heat, and with more mass, we're gonna have a lower specific heat if our amount of heat added or removed is the same. Thank you very much. That concludes our video on latent heat transformation and the three ways that heat is transferred between two substances. Thank you so much. Once again, if you have any questions, please put them down below and I will get to you as soon as possible. Have a great, beautiful, and wonderful